Math 1314, Tyler Junior College, section 3.3, dividing polynomials, remainder and factor theorems. In this final video of the series, we're going to come full circle. In the first video, we were discovering a way to factor a polynomial that did not succumb to previous factoring techniques on the presumption that we knew one of its factors. Recall that if we know one factor, we can do a division problem to find the other. We even cited the factor theorem in the first video. The factor theorem stated that x equals c is a zero of f of x if and only if x minus c is a factor of f of x. So zeros and factors go hand in hand. As we solve this, I'll remind you why they go hand in hand. But here's an example of how we can capitalize on the factor theorem. Let's just solve this equation. 2x to the third power minus 3x squared minus 11x plus 6 equals 0. Given that x equals 3 is a zero of the function f of x equals 2x to the third power minus 3x squared minus 11x plus 6. In other words, the function is the left side of this equation. How can knowing one zero help us find all zeros? Answer: because x equals 3 is a zero of this function, this implies, because of the factor theorem, that x minus 3 is a factor of the function, which means it divides evenly. But this implies that the answer to the function divided by x minus 3 is the other factor that goes along with x minus 3. So let's do a synthetic division problem. And we better get a remainder of 0 since it's a factor. So let's divide the function by x minus 3. So if we divide it by x minus 3, what number would we put in the box? 3. Remember, change the sign of the divisor's constant when you set up the box number. The top row would be the coefficients of the dividend, which are the coefficients of the function. So 2, negative 3, negative 11, and 6. And here goes the synthetic division. Bring down the first number, multiply by the box. 2 times 3 is 6. Add, negative 3 and 6 is 3, multiply by the box. 3 times 3 is 9. Add, negative 11 plus 9 is negative 2, multiply by the box. Negative 2 times 3 is negative 6. And as expected, when we add the last column, we get a remainder of 0. By the way, we should have got a remainder of 0 by the remainder theorem. Remember, being a 0 of a function means that substituting the number into the function gives you an output of 0. But the remainder theorem says that this output should match that remainder, and it did. So everything is lining up as it should. But how are we going to finish solving this equation? Well, here's something that will be repeated a lot in the next series of videos. If you have a successful synthetic division problem, and by successful I mean the remainder is 0, you have found two factors. One is what you divided by. The other is the quotient, the bottom row. What does this bottom row represent? Remember that the degree of the quotient is 1 less than the degree of the dividend, and the dividend was the function. So since the function had a third degree, the quotient will be second degree. It will start with x squared, and so this 2 represents 2x squared, plus 3x minus 2. That is what the function factors into. That's what's currently set equal to 0, so we set it equal to 0. Now, are we out of the woods yet? No. We're factored, which means we can set each factor equal to 0, but you should ask yourself, can I factor this further? Now, being a quadratic equation, I could get out the quadratic formula, but I'll tell you right now that this one will factor. If you choose to use the quadratic formula, once you reduce it to a quadratic polynomial, then that's okay. But this will factor, if you give me a second. I know it's 2x and x. I know it's 2 and 1. The 1 should be negative and the 2 should be positive. Let me FOIL it. Yes. And now that it's completely factored and equal to 0, we can just set each factor equal to 0 and solve. And this is the reminder about the factor theorem. Every 0 comes from a factor, every factor produces a 0. What would the other two zeros be? Well, without dilly-dallying, if we solve 2x minus 1 equals 0, we get x equals 1/2. And if we solve x plus 2 equals 0, we get x equals -2. So the factor theorem is really handy if you already have a 0. If you have a 0, you can turn it into a factor. The factor will set up a synthetic division problem. Poor zeros having an identity crisis. I'm a positive 3. I'm a negative 3. I'm a positive 3. I can't make up my sign. There's a rule for when you should change the sign. I'll say this a lot in the next series of videos. But the rule for changing the sign between 0, factor, and box number is the sign changes anytime you go in or out of the factor. In or out of the factor, the sign changes. In or out of the factor, the sign changes. If you do not go through the factor, you do not change the sign. So the sign only changes when it involves going in or out of the factor. But yeah, if you're given a 0, then we can use that to do a division problem to find two factors, the divisor and the quotient, and then continue solving. But this raises one red flag, one huge red flag. If you ask me to solve something, you don't usually tell me what one of the answers is. In other words, how would you do this problem if I erased everything after the equation? Well, that would be a problem, because by telling you a 0, I'm telling you a factor, which means I'm telling you a box number guaranteed to give a remainder of 0. But if I don't give you any of that, then I don't give you a box number, which raises a really good question. How do you solve this if I don't tell you one of the zeros? Well, it requires a little bit more work, but let me just leave a little cliffhanger for the next series of videos. All three of these rational zeros, rational meaning that they're ratios of integers, some of which reduce to whole numbers and integers, some of which don't. But every rational 0, the 3, the 1/2, the -2, is hiding somewhere in the original function. So in the next series of videos, we're going to tackle the question, how do we start solving an equation using synthetic division if I don't give you a hint as to what to put into the box number? Dun, dun, dun.